I go ahead and start recording here. The first thing that we're actually going to do here is we are going to go into our notes and look at a little bit with respect to Gibbs free energy. Okay, so I'm going to switch off of the Elmo projection of the problem set here, and we're going to move over to letting you guys see what's on my computer screen. Okay, so we're going to switch images here. All right, so now you guys are going to see what's on my computer screen, which is the notes for chapters 5 and 19. Okay, so here we go. So in 5th and 7th periods yesterday, we were talking about, we finished up, I guess it was chapter 5, on the various ways to calculate theoretical values for the delta H for a reaction. And so we had 3 different ways to calculate the delta H for a reaction. We had Hess's law, which was adding together thermochemical equations to get a delta H. We also had calculating delta H values from the heats of formation. So that was that equation, what was it? Delta H for the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Okay, and then we had yesterday the other form, the third form of calculating delta H for a reaction, which was using bond enthalpies. Those of you that are in 4th period, you're going to see those 3 different techniques in class today. Okay, those of you that are in 4th period, you've already seen the first 2 methods, but you haven't seen yet the one about using bond enthalpies to calculate the delta H for a reaction. Okay, and then also in 5th and 7th periods yesterday, we were talking about or doing introductions to changes in entropy, which is the level of randomness or organization of a system. And we found some different ways to calculate the delta S, or the change in the entropy for a given reaction. Okay, the last thing that we do in this particular unit is look at what's known as Gibbs free energy, which is what you see up here on the screen right now. Okay, so we looked at, we found yesterday for 5th and 7th periods again, a way to calculate delta S, the change in the entropy of a system, using, once again, the products minus reactants equation. And we did some of these sample problems 12 through 16. And again, those of you in 4th period, you're going to see me do that today in class. And now what we're going to look at is Gibbs free energy. Now, Gibbs free energy is what we use to calculate whether or not a given process is spontaneous or not spontaneous under the conditions that are specified. Now, what Gibbs free energy does is it actually looks at the interplay of the 3 driving forces behind chemical reactions. Those 3 driving forces are the change in the reaction energy, also known as enthalpy. So that's this right here, your delta H, as well as the change in the entropy of the system, which is your delta S. And then the third driving force for a chemical reaction would be temperature. So Gibbs free energy takes into account all 3 of those factors. Okay, Tommy? The temperature, it is capital T, so here it must be in Kelvin. Okay? And you will see that because the units that we're going to see for delta S right here, the units for delta S are going to be joules per Kelvin. So with that T in front of the delta S, that means that the temperature would have to be in Kelvin in order to get those units to cancel out. Does that make sense? Okay, so that was a great question. So Gibbs free energy, which is symbolized by this letter delta G, is equal to delta H minus T delta S. Now this equation right here is what is known as the Gibbs-Helmholtz equation. You're not going to need to know that name, but that's what it's called, the Gibbs-Helmholtz equation. So the Gibbs-Helmholtz equation allows you to calculate the change in the Gibbs free energy of a reaction looking at those three factors. The enthalpy factor right there, the entropy factor right here, and the temperature. Am I making sense? And then we can predict whether a reaction is spontaneous or not spontaneous by looking at the sign of delta G. Okay? Now, if the sign of delta G is negative, so right here, when delta G is negative, that tells us that for the reaction written in the direction that it is, that process is spontaneous, meaning that it will occur without continuous outside intervention. Okay? If delta G for a given reaction is positive, then that tells us that the reaction is not spontaneous in the direction written. And then the third option is, well, what if delta G is equal to 0? If delta G is equal to 0, then what that represents is that the reaction is at equilibrium and there is no tendency for the reaction to go in either direction, meaning it's not favoring the right nor is it favoring the left. Does that make sense? Okay, so those are the three options. Delta G can be negative, it can be positive, or it can be equal to 0. If it's negative, it's a spontaneous process. If it's positive, it's not a spontaneous process. And if it is 0, then the system is at equilibrium. Okay, now you're going to notice that there are two different Gibbs-Helmholtz equation. What's the only difference between those two equations that you see? The delta G equals delta H minus T delta S. Yeah, what we see is one of them has the superscripts and one of them does not. And the superscripts, you guys, just represent standard state conditions. Okay? And so standard state conditions, what that implies is that if we are talking about gases, that all gases are at 1 atmosphere of pressure, that the temperature is exactly 25 degrees Celsius, which is standard room temperature, and if we are talking about solutions, that the solutions are at a concentration of 1 molar. Okay? So it just specifies a specific, set of reaction conditions. Okay? Now, another way to calculate delta G, this equation should start looking very similar here, is to calculate the sum of the Gibbs free energy of the products and subtract the sum of the Gibbs free energy of the reactants. Now, this, of course, assumes that you know what the Gibbs free energy of all the reactants and the products is equal to. Okay? Now, question is, where might we find these Gibbs free energies for our reactants and products? Anybody have any ideas? We're all distracted right now because Annie has walked in with a great big set of balloons that says, "Happy birthday!" All right, you guys. So if we're going to use this last equation, products minus reactants, what does that assume? That we're given those, and where do you think that we're going to find them for solving the problems that we're going to be doing? The chart. Appendix 4. All right, the select thermodynamic data, where the first column is the delta H, the heats of formation values, and the second column is the entropies, and the third column on Appendix 4 is the Gibbs free energy of formation. Okay? So depending, on what kinds of information we're given, that's going to affect which one of these equations we're going to use to solve for the delta G of a reaction. Am I making sense? Okay, so what I'm going to do here is I'm going to switch over from the notes to our sample problem packet because what you're going to see here, if I scroll down, I'm going to take my pen off here and just scroll down here. Sample problems. It says we're going to be working a bunch of sample problems. Do you guys see that? Okay, so I'm going to pause this recording